In this section, we transition to the study of material testing. As part of many engineering and engineering technology programs, college students are typically educated in several areas of applied physics, one of which is called deformable body mechanics. All solid bodies experience some degree of deformation when subject to externally applied forces, such as tension or compression. As you might remember, deformation is a change in dimension that is caused by the application of force, pressure, heat, or any other physical phenomenon. Deformations are also accompanied by stress within the object, which increases as the load also increases. As you will see today, engineering stress-strain diagrams show the relationship between the stress and the amount of strain that a material will exhibit under a given load. Engineers use these graphs to make important decisions about which materials to use and to determine how much loading the materials can withstand without suffering permanent damage or failure. Let's begin by considering some important questions. How do engineers know how big a building support column should actually be? Or why is it that support beams should be made of steel instead of glass? How do engineers know what weight limit to place on an elevator? Or how to determine a maximum load that a car can carry? The answer to all of these questions are why engineers test materials as well as analyze them to ensure that they meet the specifications and quality standards before they ever leave the manufacturer. Testing takes place to ensure reproducible results of materials, and they can be classified one of two ways. That testing could be considered static testing or dynamic testing. With static testing, it involves applying a load gradually up to the point of failure. This type of testing helps eliminate unwanted effects such as vibration. Both tension and compression testing usually involves the application of static loads. Dynamic testing, on the other hand, involves sudden and extreme loading or repeated loading over large numbers of cycles. Dynamic tests are performed to determine how many times a material can be loaded and unloaded before it fails due to fatigue. Fatigue is the deterioration of a material as a result of repeated loading and unloading. An example of a dynamic test would involve a car manufacturer who's testing the durability of their seatbelts by clicking and unclicking the seatbelt mechanism over and over and over again to see how well it will properly function before jamming up. For the purpose of gathering data, materials are subjected to a variety of standardized destructive tests. Destructive testing involves loading a test specimen to the point of structural failure while collecting data that indicates a material's mechanical properties. There are so many different kinds of destructive tests, with three of the most common being a tensile test, which looks at how a certain material behaves when a tension force is applied, a compression test, which looks at how certain materials behave when a compression force is applied, and the third is a hardness test, which looks at how much materials are indented when a static load is applied. The evaluation of a material based on the data collected will help us as engineers in determining whether or not a material has the strength to withstand specific loads, what the ultimate tensile strength of a material actually is, and how the material deforms or fractures over time. For this lesson, we will focus specifically on the static testing of materials. When it comes to testing materials such as woods, ceramics, and especially different types of plastics and metals in the manufacturing industry, they're most often conducted using a tensile test. But in order to conduct a tensile test, engineers often require the use of a machine called a tensometer. A tensometer device consists of two grips that hold each section of the test material in place. Tensometer instruments can create the force through the use of either a screw or a hydraulic ram, which are powered by mechanical or electrical means. The amount of stretch that a material has when it's under strain provides important information about the material's tensile strength and fatigue strength. Dog bone material samples are primarily used in tensile tests. The sample has a shoulder at each end and a gauge section in between. The shoulders are wider than the gauge section, which causes a stress concentration to occur in the middle when the sample is loaded with a tensile force. This stress concentration ensures a higher probability that the sample will rupture away from the ends. When the rupture of a sample occurs in the midsection, we know it's going to be attributed to the material reaching its maximum tensile strength. Whereas if the sample was to rupture at one of the ends or at the grip itself, The failure may be attributed to improper loading or pre-existing defects in the material. Therefore, a dog bone sample is designed to ensure the highest probability that the sample will fail due to maximum tensile loading. To eliminate test results based on sample size, we calculate stress. Stress, also known as axial stress, is a reaction that occurs within an object that provides resistance to dimensional changes brought on by applied loads such as tension and compression. Stress is represented by the Greek letter sigma, and it's mathematically defined as the intensity of a force F per unit cross-sectional area A within a structural member. As a quick example, let's think of cables on an elevator. A team of engineers had to determine what kind of material those cables should be made from and how large their diameters would need to be in order to withstand the stresses that build up inside the cables. If the cables are too thin, they'll snap because of excessive stress levels that result from too much load. If the cables are too thick, then they won't easily bend around the pulley wheel as the elevator moves up or down. When too much stress builds up inside an object, the end result is permanent change in shape or fracture. Given a constant load, the amount of stress that builds up within a structural member will decrease as the cross-sectional area of that structural object increases. Therefore, spreading a force out over a larger area will result in less force per unit area and therefore cause a lot less stress. In this example, we're asked to calculate the stress in a dog bone when 430 pounds of force is applied. Since dog bones are cylindrical, to find the cross-sectional area, we need to use the formula pi r squared. So sigma equals 430 pounds of force divided by 0.0123 square inches, and we get a stress of 35,000 psi. Note the common U.S. customary system unit of measurement for stress is pounds per square inch, or psi. Determining a material's mechanical properties in tension or compression involves analyzing the relationship between the growing amount of stress that builds up within a material as the applied load increases and the change in strain that the material exhibits. Strain, which is represented by the Greek letter epsilon, is how much a material stretches for every unit of original size. Materials exhibit different types of strain depending on the material itself, as well as the type of load that the material is encountering. Strain is mathematically defined as the change in length, delta, known as elongation, divided by the original length, which is represented by L sub 0. Keep in mind that all objects deform when they experience an external load, even though the amount of elongation or stretch may be unrecognizable to the naked eye. If a 10-inch long plastic rod is subject to a tensile force that stretches it to a final length of 11 inches, then the resulting elongation or stretch is the change in length that is equal to 1 inch. A change in length that results from tension is recorded as a positive value because the object is expanding. A change in length that results in compression is recorded as a negative value because the object is decreasing in length. The unit of measurement for strain is inches over inches in the U.S. customary system. Returning to the previous example of the 10-inch long plastic rod, if the total change in length is 1 inch, then the axial strain will equal 0.1 inches over inches, or 10%. This means that 0.1 inches of elongation occurred for every 1 inch of original length, which represents a 10% increase in the length of each unit as well as the overall length of the member. Strain values can be very small, especially for metals. They are often represented in engineering or scientific notation, or even as percentages. In this example, we're asked to calculate the strain in a dog bone with an elongation of 0.0626 inches. To do this, we need to take our elongation, delta, which is the amount of stretch, and divide it by the original length, L sub 0. Here we get 0.0625 divided by the original length of 1 inch to get a strain of 0.0625 inches over inches. Material engineers perform standardized tests on material samples to determine the amount of elongation that it will exhibit when subject to specific types of load conditions. The results of such tests take the form of force elongation diagrams, which is graphs that show the relationship between the force and the elongation. Make note that the force is represented on the vertical axis and the elongation or stretch is represented by the horizontal axis. It is inefficient and cost prohibitive to perform force elongation tests on every structural component that make up an engineering design. Therefore, engineers communicate the force displacement test results of standard size material test samples in a form that's applicable to designs of any size. By taking into consideration the original cross-sectional area, as well as the original test length of the test sample, force and elongation values can be converted to stress and strain values respectively. When plotted on a graph, they form an engineering stress-strain diagram. Though the shape of an engineering stress-strain curve is identical to its corresponding force elongation diagram, the values of stress and strain are independent of the test sample's original shape and size. Therefore, two test samples that are made from the same material but different sizes or different cross-sectional areas and original lengths will generate force elongation diagrams of identical shape but of different magnitudes of force and elongation. When converted to engineering stress-strain diagrams, both samples will theoretically display identically shaped curves with identical magnitudes of stress and strain. For this reason, designers use the engineering stress-strain curves to make informed decisions on the types of materials to use in the design of structural components. Different materials produce different stress-strain curves, many of which are different in appearance. The following slides will provide explanations of the important points on an engineering stress-strain diagram related to a curve that is produced by the material under uniform tension. As a material is loaded in tension, it will exhibit a buildup of stress accompanied by an increase in strain. At the early stages of this loading process, a material will experience elastic deformation. Elastic deformation is the change in size or shape of an object under an applied load from which the object will return to its original dimensions when unloaded. The idea is very similar to the behavior that a rubber band exhibits when stretched. Regardless of the time over which the load occurs, if the load is removed from the material while it's in this range of elastic deformation, the material will return to its original dimensions. Virtually all mechanical and structural designs that must withstand temporary loads are designed to take advantage of this mechanical property. For most engineering materials, such as metals and plastics, the relationship between stress and strain starts off as a constant ratio, and it results in a straight line from the origin to a point known as the proportional limit. This point is referred to as the proportional limit because the proportionality between stress and strain no longer exists once it's exceeded. Elastic deformation takes place only between the origin of the graph and another point called a yield stress. Consequently, this region of the graph is referred to as the elastic range. As you can see in this demonstration, if the load is removed while within its elastic range, the test sample, which in this case is the dog bone, will return to its original length. And we call this the elastic range because the response to the dog bone is elastic or recoverable. The elastic limit is the uppermost stress of elastic behavior. Make note that the elastic and proportional limits are located almost at the identical positions, with the elastic limit being slightly higher as it's located at the yield stress point. This is because the elastic limit is the strain below which the material can regain its original shape if the forces are released. Therefore, it doesn't matter if the stress-strain relationship is linear or not. When a material is stressed beyond its yield stress point, it will experience permanent change in shape. As a result, the tensile test specimen is now longer than it was prior to loading or even after the removal of the load. If you have ever bent a paperclip out of shape, then you have generated a stress within the paperclip that caused the material to yield. If you tried to return the paperclip to its exact original shape, then you probably realized that it could not be done. When a material is loaded beyond its yield stress, again, it will experience permanent dimensional change or permanent change of its shape, and it will become evident once the load is removed. Unfortunately, most materials do not have a well-defined yield stress point. Since few materials have a yield stress point that's easily identified on an engineering stress-strain curve, there is a mathematical process called the offset method that's used to determine an arbitrary yield stress point on any given engineering stress-strain curve. The process involves drawing a line parallel to the linear portion of the engineering stress-strain curve, beginning at a strain value of 0.2% on the x-axis. The point where the offset material line crosses the engineering stress strain curve is known as the offset yield stress. The yield point is very important to engineers who design mechanical and structural components because it serves as the threshold limit. Engineers understand that all materials change shape under load. By predicting the greatest load that a structural member will encounter and keeping the material's yield point in mind, an engineer can ensure that his or her design will act like a spring and return back to its original shape when the load is finally removed. This picture on the slide provides a nice summary of the past few slides mentioned. As I said before, if a component is intended to return back to its original shape upon unloading, then the yield stress of the material from which the component is made from will usually serve as the actual stress limit. The engineer will decide on an allowable stress limit within the elastic region of the material's engineering stress strain diagram to ensure that the design will avoid structural failure from situations such as accidental overloading. The ratio between a material's actual stress limit and its allowable stress limit is referred to as a factor of safety. The structural failure of an aircraft component, for example, can have a far more disastrous result than the structural failure of a component on a piece of farm equipment. As such, factors of safety can vary, depending on the application. Some factors of safety are indicated by codes, which are standards that are enforceable by law. In many cases, factors of safety are based on many years of experience and time-tested practice within the field of engineering. If an appropriate material and factor of safety have been determined, then the allowable stress can be calculated. The geometry of the structural component along with the allowable stress are then used to calculate the maximum allowable load. Every component in a mechanical system acts like a link in a chain, with the weakest link determining the maximum load that a system can withstand. That's why engineers establish maximum weight limits for their designs. The next time you're in an elevator, look for the plaque that identified the elevator's maximum load capacity. Also look on a driver's side door jamb on your family's car to find the sticker that gives the gross vehicle weight rating. Both of these maximum weight limits were established by engineers to ensure that the stress values that are experienced by the various mechanical components will not exceed their yield stresses. The slope of the engineering stress strain curve within the elastic region of the graph is called the modulus of elasticity and is represented again by the capital letter E. Recall that the modulus of elasticity is the measure of stiffness, or the ability to resist stretching when a load is applied. The modulus of elasticity can be found by dividing stress, sigma, by the strain, epsilon. The unit of measurement for the modulus of elasticity is PSI in the U.S. customary system. Using the change in stress and strain as measured from the origin of the graph up to the proportional limit is an easy method for calculating the modulus of elasticity. It is not unusual to see elastic modulus values in the millions of PSI for materials such as aluminum, brass, and steel. Materials such as rubber, neoprene, and silicone offer the most extreme examples of mechanical property called elasticity. All materials experience some degree of deformation when subject to an applied load. If the load is small enough, then the material will return to its original shape once the load is removed. Therefore, elasticity is a mechanical property that allows a material to return back to its original dimensions once the load has been finally removed. Think of it like this. Every time you drive over a bridge, the steel and concrete materials are deforming to some small degree as a result of tension and compression forces. In other words, the bridge is changing shape. Once you cross the bridge's components return back to its original sizes as the result of the elastic nature of its materials. A material that exhibits a large yield stress and a small modulus of elasticity will behave like a rubber band. In lieu of an engineering stress-strain diagram, a material's elastic quality is represented by a value known as the modulus of resilience. This represents the area under the material's engineering stress-strain curve between the origin and the yield point. The modulus of resilience, represented by the capital letter U, is defined as the measure of the amount of strain energy per unit volume that a material will absorb without experiencing permanent deformation. The value of the modulus of resilience is expressed usually in terms of PSI. To calculate the modulus of resilience, we take 1/2 times the yield stress times the yield strain. In an easy example to understand the modulus of resilience, think in terms of a car bumper. A car bumper is made or created so that it can absorb energy upon impact. Well, we want to know how much impact that car bumper can withstand before it's permanently deformed. Plastic or permanent deformation occurs beyond the yield stress point and continues to the point of fracture or total structural failure. This means that any change in shape past the yield stress point will result in permanent dimensional changes on the part of the structural member itself, even if the load is removed. Some designs require that a material be permanently deformed in order to achieve a desired shape. For instance, bending conduit for electrical wires, drawing stainless steel sheet metal to form kitchen sinks, and pressing sheet metal into the form of a car body panel are all examples where materials must be stressed beyond their yield stress points in order to achieve a desired shape. Plastic deformation is characterized by a noticeable amount of unit strain with relatively little increase in stress. As this occurs, the material becomes harder. Eventually, the material reaches its ultimate stress, which is the ultimate amount of stress that a material can withstand without failing. Beyond this point, the material will exhibit necking, which is a visible decrease in cross-sectional area at the location where fracture will eventually occur. Consequently, the region on an engineering stress-strain diagram between the ultimate stress and the point of fracture is known as the necking region. An easy example to understand necking is to think back to if you ever, as a kid, played with Play-Doh or Silly Putty, you probably remember at some point as you pulled that material further and further apart, it began to give way and required less effort to stretch it out a lot more. It was at this time where the necking period began. And you can see here, if a continued force is applied, the necking will continue until finally fracture occurs. Where the fracture occurs is considered the failure point. Now, the time period that it takes for a material to finally fail is going to be based on its ductility. Recall that ductility is the amount of plasticity before fracture. The greater the ductility, the more the material can be deformed over time. As you can see in the 3 pictures below, tensile test specimens that are made from ductile metals, such as aluminum and copper, will experience significant reduction in cross-sectional area and exhibit a so-called cup and cone fracture pattern. Unlike brittle materials that show little, if any, reduction in the cross-sectional area where fracture occurs, and they exhibit a more flat and uniform fracture pattern. So based on these 3 pictures, you would assume that the first 2 materials are more ductile than the one that's all the way on the right, which would be considered a more brittle material. At the top right corner, you can watch a tensile test in action. So with that said, engineers look for materials that exhibit certain mechanical properties when they design solutions to structural problems. Mechanical properties are attributes that all materials exhibit to some degree when subject to external forces. Such properties include brittleness, ductility, elasticity, hardness, malleability, strength, and toughness. Strength is a general term that refers to the material's ability to resist applied loads. Materials such as stone and steel exhibit great strength, which is why they're used in the construction of buildings. Various stress points along the engineering stress-strain curve are often referred to with the term strength, such as yield strength and ultimate strength. However, this practice is not technically correct because the concept of strength is directly related to force, not stress. It's more appropriate to refer to points on the force displacement diagram using the term strength and points on an engineering stress-strain diagram with the term stress. As mentioned previously, ductility is the term that describes a material's ability to experience plastic deformation through tension without breaking. The most common example of this is drawing a material out into a shape of a long, thin wire. Metals such as copper and brass are very ductile materials that are made into wires for use in electrical applications. Other metals such as low-carbon steel and aluminum are also fashioned into long wired for use in both electrical and structural applications. Elastomer materials such as rubber are not considered ductile because of the large deformations they experience under loads that are not permanent. Materials such as gray, cast iron, concrete, and glass do not exhibit plastic behavior. Such materials are characterized as brittle because they experience fracture at or shortly after their yield point is exceeded. Therefore, brittleness is a mechanical property that causes a material to fracture at relatively low strain values. Brittle materials like glass, concrete, and cast iron have stress strain curves that show fracture occurring shortly after the yield point, as you can see at the picture above. Malleability is another mechanical property that is similar to the concept of ductility. A malleable material is able to resist change in shape under applied compressive loads without breaking. Therefore, malleability is a mechanical property that allows a material to experience plastic deformation through compression without breaking. The most common example is pounding or rolling a material into a shape of a thin sheet. Gold, copper, and aluminum are naturally malleable materials. Note, however, that not all materials that exhibit high degrees of malleability will be equally ductile. For instance, lead is a malleable metal that is not considered ductile. Toughness refers to a material's ability to absorb energy that results in permanent deformation. This material property can be thought of as a combination of both strength and ductility. For instance, the head of a hammer must be made from a tough material, or it would shatter on impact with another hard material. Though it does not provide the accuracy of an impact test, the total area under a material's engineering stress strain curve will give the engineer an indication of how a material will perform under impacted conditions. This area is known as the modulus of toughness and is represented by the capital letter U, which is defined as the amount of work that can be done on a material per unit volume without causing fracture. A material that exhibits a large modulus of toughness is more likely to withstand the force of a sudden impact without failure. The value of the modulus of toughness shares the same units as the modulus of resilience, represented usually by pounds per square inch or psi. Some materials can withstand much larger compression stresses than tensile stresses. One example is concrete, which is used extensively in the foundations of buildings and bridges. Compression tests are also conducted in a universal testing machine. Compression samples are usually made in the form of cylinders that have a 2-to-1 length to diameter ratio. For example, a standard concrete test sample is 6 inches in diameter, 12 inches long, and has been cured for over 28 days. As the material is loaded in the compression, the change in force and deformation is converted and graphed on a stress strain diagram. The shape of the curve is very similar to that of the tensile test, where the distinct linear region is evident up to the proportional limit. From brittle materials like concrete, fracture occurs around the yield point. If you have ever had the chance to watch real concrete samples being tested till its failure point through compression, make sure to keep your distance because the material has a tendency to explode. You can watch the video in the upper top right corner of a compression test on a concrete cylinder. Hardness is a mechanical property that gives a material the ability to resist surface penetration, scratching, or wear. It is most associated with metals and ceramics, though it is also a property that's exploited in the design of many composite materials. Hard metals such as glass also tend to be brittle. You may have heard that a diamond is a girl's best friend, but did you know that a diamond is actually the hardest known naturally occurring mineral? Diamonds are so hard that they can scratch almost all other materials, which is why they're used in the ends of many drill bits. Diamond-tipped drills are often used for mineral exploration and core sampling. To verify that a material has the proper hardness, it may be placed through one of several different types of hardness tests. Most of these tests involve indenting the material using a specifically shaped tool under a given static load and measuring the resulting indent of its shape. Two of the most common hardness tests that are used are the Brinell and Rockwell test. A Brinell hardness test involves using a special machine to push a hardened steel or tungsten sphere into a test sample where the diameter of the resulting indentation is used to calculate the material's hardness. Feel free to watch the video in the bottom right corner of a Brinell hardness test. A Rockwell hardness test involves using a diamond-tipped cone that is forced into the test sample by a predetermined load, where the depth of the penetration is measured from the resulting indentation and it's compared to other materials' hardness. Feel free to watch the video in the bottom right-hand corner of a Rockwell test.